Hello everyone. We have been discussing types of reactions. So last lecture we discussed precipitation and did a stoichiometry problem on it. So in this lecture we have been discussing what a neutralization reaction is. We saw a video on it. And we're in this lecture we are going to talk about strong versus weak acids and bases. And then we are going to work on one stoichiometry problem on neutralization. Okay, here we go. It's a good idea to remember these strong acids. You basically have 8 of them. Okay, so there are many more, but these are the common ones that you have to remember. These are your 8 strong acids. If you see a pattern here, hydrochloric, bromic, iodic, these are strong, but hydrofluoric acid is weak. Okay, your nitric acid and sulfuric acid. These are often used in the lab, so you should remember these are strong acids. Okay, chloric and perchloric are again strong acids. The rest of them are weak. Acetic acid, which is a major component of vinegar, is a weak acid. Phosphoric acid, it's used as a preservative in soft drinks. So this is weak acid. Carbonic acid, so you have carbon dioxide dissolved in water, you get small amounts of carbonic acid, which is a weak acid. And this is again a component of soft drinks. The other acids like us acids and hypo-us acids, those are going to be weak as well. For example, phosphorus or sulfurous, chlorus, these are going to be weak acids. Now coming to bases, as you can see here, bases are substances that contain hydroxide ions. So they're going to produce hydroxide ions in water. So if you dissolve lithium hydroxide in water, it's going to produce lithium ions and hydroxide ions. Okay, and since it produces hydroxide ions, that's what makes it a base. Remember the difference. Acids, they contain protons, so they're going to release protons when you dissolve them in water. Bases, on the other hand, release hydroxides. And here are common strong bases that you must remember. All group 1 hydroxides are strong. Lithium, sodium, potassium, rubidium, cesium, all these are strong bases. I didn't mean to put those here. Sorry about that. Okay. Now coming to group 2, only the calcium, strontium, and barium hydroxides are strong bases, okay? Weak bases. Ammonia is a classic example of a weak base. The formula for ammonia is NH3, and it's a weak base. Ammonia, you know, is a component of household cleaning products. It's a base. Now, other derivatives of ammonia, such as amines, these are bases. So the R here stands for any carbon group, okay? So for example, if you have methylamine, methyl means one carbon containing group, okay? So, so one carbon, and this carbon, remember carbon always makes 4 bonds. So one bond is already done. So the rest 3 bonds are with hydrogen. So you just fill in the hydrogens. So this is called methylamine, and it's a weak base. For example, you have ethylamine. Ethyl means 2 carbons, just like you have 2 carbons in ethanol, okay? So you have 2 carbons attached to this NH2 group. That's ethylamine. So think how many hydrogens should be on the carbon in the center. There should be 2 hydrogens because carbon always makes 4 bonds. So here there should be 3 hydrogens. Okay, so this compound C2, H1, 2, 3, 4, 5, C2, H5, and H2. That's ethylamine. So these kind of substances with the NH2 group, this group is called amine group. So these are called amines, okay? They're all weak bases. They are basically derivatives. You can think of them as derivatives of ammonia. So what are strong acids and weak acids? What's the difference between them? So basically, a strong acid or a base is the one that dissociates completely. In other words, there is 100% dissociation. So let's say you have hydrochloric acid, HCl. HCl dissociates to protons. and chloride ions in water. Okay, so you can write aqueous HCl is aqueous H plus aqueous chloride. This acid is a strong acid, so it's going to dissociate completely. What that means is if you have 100 molecules of HCl, all 100 are going to break apart to produce 100 protons and 100 chloride ions. So if you zoom into a bottle of hydrochloric acid, you're not going to see HCl. All of it has dissociated, 100% of it. All of it has dissociated and converted to H plus ions and chloride ions. So for 100 molecules that dissociate, there will be 100 protons and 100 chloride ions generated. Okay, so remember, hydrochloric acid doesn't contain those HCl molecules anymore. We have protons and chloride ions in a bottle of hydrochloric acid. Now, on the other hand, a weak acid like acetic acid, so acetic acid is CH3COOH, which can also be written as C2H3O2H. That's another way of writing the same thing. This dissociates into only the hydrogen attached to the oxygen is the one that's going to dissociate. Okay, so you get, so this bond breaks and you get protons plus C2H3O2 negative. That's acetate. This is acetic acid. Acetic acid, which is a major component of vinegar, is a weak acid, meaning it dissociates partially. And we show that using this double arrow. Okay, the reaction is going to go backward as well. As these ions are generated by breaking these two can combine together also and make your molecular acetic acid. So if you zoom into a bottle of acetic acid, you're going to find lots of acetic acid acid molecules, but only a few ions. The reason is it dissociates partially. So if you have, let's say, a billion of these, okay, maybe a few of them, maybe only 100 of them. So 100 of them will be gone and they will convert to these products. Only a few of them are going to dissociate. That's the nature of weak acids and bases. They dissociate partially. Okay. Now, for a strong acid, strong base reaction, so if you have a strong acid plus strong base neutralization reaction, think about what is the net ionic equation going to be? Net ionic equation. So let's say you have HCl plus NaOH. You can take other examples of strong acid and strong bases. This is going to produce NaCl, salt, plus water. Okay, so your water will be liquid. The other ones are dissolved in water, aqueous. Okay, if you think about what they truly are, HCl, since it's a strong acid, you don't have hydrogen and chlorine attached anymore. So you have H plus and Cl minus. They have dissociated. So you could break apart into ions. Same thing for the strong base. Since it dissociates completely, you can break it apart into ions. What you have inside the solution are ions. It's no longer the sodiums and hydroxides are attached together. Okay, sodium hydroxide dissolves in water to produce sodium and hydroxide ions. Similarly, your salt dissolves in water, so you get sodium and chloride ions in the solution. So you can cancel out the chloride and you can cancel out the sodium. And look at your net ionic. It's H plus hydroxide going to water. Okay, water is a molecular substance. Water doesn't dissociate into ions. It's a poor conductor of electricity. You don't have many ions in water. Okay, only ionic substances, you break them apart because ionic substances that dissolve in water dissolve by breaking apart into ions. So that's why you basically separate them. This is a strong acid. Okay, strong acids dissociate completely, so that's why you can ionize it. And when you cancel out, you are left with this equation. So that's the net ionic equation for any strong acid base reaction. Okay, Protons from the acid react with the hydroxides from the base to create water. That's what is happening at the net level. Now, coming to performing stoichiometry, remember this chart. Anytime you have volume of a solution, you can use molarity and volume to get to moles. And once you have moles, that's the heart of stoichiometry, you can go from moles of one substance to moles of another substances. And when you have solutions, you're dealing with volume and molarity to convert to moles. So remember that. And we are going to work on a stoichiometry problem to find the molarity of an acid. So here's the sample problem on stoichiometry of between acids and bases. So this question asks you, what is the molarity of sulfuric acid solution if 25 milliliters of the acid solution requires a minimum of 15 milliliters of 0.01 molar sodium hydroxide to neutralize it? So you're basically neutralizing sodium hydroxide and sulfuric acid. And somebody found out that it takes 25 milliliters of the acid to neutralize 15 milliliters of 0.01 molar concentration sodium hydroxide. Using this information, how can you find the molarity of the sulfuric acid solution? Well, since this is a reaction between those two, you have to set up a balanced equation. Most students make a mistake here. They see volume 1, concentration 1, and volume 2. They jump to M1V1 is equal to M2V2. Remember, M1V1 is equal to M2V2 is a dilution equation. There's no reaction going on there. Okay, you're not just diluting sulfuric acid here. Okay, it's a reaction. And when you have a reaction, you have to use the stoichiometry. You have to use the molar ratios in which sodium hydroxide and sulfuric acid react. So let's get the balanced equation first. So you have sodium hydroxide reacting with sulfuric acid. And this is an acid-base reaction, base reacting with acid. So your products are going to be salt. The salt here is sodium sulfate. But be careful, you have to write the correct formula for sodium sulfate. Sodium ion is Na plus. Sulfate is SO4 2 negative. Okay, so if you do crisscross, you get 2 sodiums for every 1 sulfate. So sodium sulfate's formula is Na2SO4. And this is your salt. In chemistry, any ionic compound can be called a salt. Okay. Plus, remember that a product in neutralization will be water. So the hydroxide from the base and the protons from the acid react together to make your water. We got the reaction. Next step number 2, balance it. Okay. Since you have 2 sodiums on the right, we need a coefficient 2 here. And what else? So here's my logic. You have 2 hydroxides, so 2 hydroxides, and you have 2 protons from the acid, 2 protons from the acid. So how many waters should you get? You need to get 1 and 2, 2 waters. So the coefficient of water should be 2 here. Okay. Now my reaction is balanced. You can check if you want. Step number 3, you're doing stoichiometry. In stoichiometry, always the heart of stoichiometry is moles. So try to find moles of one substance in this problem and then convert it to moles of another substance using the molar ratio between them. Okay, using the molar ratio between them. So whose moles can you find? Sulfuric acid, we know only the volume. There's no way to calculate moles. But if you look at sodium hydroxide, You know the concentration, it's 0.010 molar, and you know the volume. So you can find moles because remember, molarity is moles over liters. So if you know molarity and if you know the volume, you can find moles. So moles will be molarity times volume of the solution in liters. Okay, so since we know the molarity of sodium hydroxide and the volume of sodium hydroxide, we can find moles of sodium hydroxide. Remember, you have to always use conversions from apples to apples, okay? So if you're using molarity of sodium hydroxide and the volume of sodium hydroxide, what you get is moles of sodium hydroxide, not any other substance's moles, okay? So moles of sodium hydroxide will be molarity, which is 0.010 molar, times the volume in liters of sodium hydroxide. So 15 milliliters, so move the decimal 3 times to the left because you have a factor of 1,000 between milliliters and liters. So that's going to be 0.01500 liters. Notice this molar unit, you can also rewrite it as moles over liter. It's the same thing. Molarity is moles over liter. So you can see the unit canceling out and getting moles. So here the moles, number of moles is going to be 1.5 times 10 to the negative 4 moles of sodium hydroxide. Okay, we completed our first part. We found moles of one substance. Now using that, we can determine how many moles of sulfuric acid it's going to react with. Okay, because we have the ratio 2 to 1. For every 2 moles of sodium hydroxide, it takes 1 mole of sulfuric acid. So if you have that many moles of sodium hydroxide, it's going to take that divided by 2 because you can see 2 moles of sodium hydroxide, okay, takes 1 mole of sulfuric acid. That's the molar ratio from the balanced equation. So moles of sodium hydroxide cancel out, and we can find how many moles of sulfuric acid reacted with it. So that's 1.5 times 10 to the negative 4 divided by 2. Do this calculation with me, and you get 7.5 times 10 to the negative 5 moles of sulfuric acid is what reacted with this many moles of sodium hydroxide. So effectively, this number is how many moles of sulfuric acid it takes to neutralize this base. Okay, so this is moles of sulfuric acid that should be used to neutralize the base. And as you can see here, this information is telling you it took 25 milliliters of sulfuric acid to neutralize the base. So volume of sulfuric acid used, was 25 milliliters, which is 0.025 liters. And this is volume used, and this is moles used. Okay, so you can see that we have converted sodium hydroxide to sulfuric acid and figured out how many moles it takes. So these moles should have been in the volume used. Okay, these moles should have been in that 25 milliliter. So since we know the moles and the volume, we can calculate the molarity. So molarity of sulfuric acid will be moles of sulfuric acid are used, moles is that one number, divided by the volume used in liters. Molarity is always moles over liters. So divided by 0.025 liters. And now you can calculate the molarity. And I got 0.025. That's giving me 3 times 10 to the negative 3. And you have to use accurate number of significant figures. As you can see, here you have 2 sig figs in this number. So this should have 2 significant figures, the final answer. So it's going to be 3.0 times 10 to the negative 3. The unit for molarity is moles per liter, which can also be written as molar. So that's your answer. That's the molarity of your sulfuric acid. So if you carefully pay attention to what's going on in this problem, we are finding the molarity of a solution. So suppose in the lab there is a bottle of sulfuric acid lying somewhere, and you want to know what the concentration of that sulfuric acid solution is, then what you do is you take sodium hydroxide of known concentration and you start reacting them both. So you estimate, let's say you took 25 milliliters of sulfuric acid, you're going to estimate how much of the base is it going to take to neutralize all of your acid. And once you have that information, you can find the molarity of sulfuric acid. We do this all the time in the lab, and it's called titration. So I'm going to talk about what a titration looks like. So in a titration, you're going to take one solution in a conical flask and another solution in the burette, and you're going to add the solution in the burette slowly into the solution in the conical flask. And this process is called titrating, and you're going to keep adding until all the compound in your conical flask has completely reacted. So you're going to stop adding when the amount of when all the moles of your substance in this conical flask has reacted. So how do you keep track of when these two substances have reacted in their stoichiometric ratios? How do you do that? So let's say, for example, we have an acid of unknown concentration in this conical flask. So let's say you have 25 milliliters of it. This is the volume of the acid that you took. And acid contains protons. So this solution in the conical flask has a bunch of protons, because remember, acids dissociate to produce protons. So that's what you have in this conical flask. Okay, so to keep track of the endpoint, you're going to add a few drops of an indicator. Indicator basically changes, it has different colors. So if you, let's say you're titrating acid and base, you can choose a phenolphthalein indicator, because phenolphthalein is colorless in an acidic solution, but it has a pink color in basic solution. So you're going to put a few drops of phenolphthalein in here, and since this is an acid, so it's going to be colorless. Okay, let's say you're titrating with a base in the burette. So the burette has base like sodium hydroxide of a known concentration. So you know its molarity, let's say 0.10 molar. What you're going to do is you're going to add the base into the acid. You're going to drop the base. Okay, chemistry is fun. We drop bases all the time. Okay, so what is a base? Base is basically hydroxide. So you're going to slowly add the hydroxides into your acid. What does the base do? The base neutralizes your protons. Okay, so as you keep adding the base slowly, drop by drop, you're going to see a pink drop because of the base added, but that base is going to disappear quickly because the hydroxide added react with your protons. So if I put one more hydroxide into the solution, it's going to react with this proton and it's going to disappear. So if I put one more hydroxide into this solution, it's going to react with this molecule of proton, and both are going to neutralize each other to make water. So as long as there is excess base still in the conical flask, the color will be still colorless. It's not going to have any color because phenolphthalein in an acidic medium is colorless. So as long as you have acid, the solution will be colorless. Okay, but once you have added enough hydroxide, so let's say I added hydroxide, it neutralized a proton, another hydroxide, so it neutralized this proton. So you kept adding hydroxides, and let's say all the acid has been neutralized. Now, when you add an extra drop of base from the burette, so let's say I'm adding this extra drop. So that extra hydroxide that you added, hydroxide ion from the base that you added, it cannot neutralize anymore because there is no acid in this conical flask anymore. Okay, so that extra one, it's going to remain unreacted. So you're going to have base in this solution now. Okay, once all the acid has been exhausted, any extra drop that you add will make this solution basic. Okay, and so what should be the color of phenolphthalein? It should be pink. So you're going to see a pink color. Okay, once you see a faint pink, that's an indication that all your acid has reacted. So you're going to stop titrating and record what volume of sodium hydroxide has been used. So let's say it used 15 milliliters, like we saw in the previous problem. Okay, that's it. There you have enough information to calculate the molarity of the acid. From these two informations, you can calculate the molarity, sorry, volume and molarity. You can calculate moles of base. And once you have moles of base, you're going to convert it to moles of acid. Moles of acid using the stoichiometric 1 to 2 ratio. And once you know the moles of acid, since you have the volume of acid, you can use these two to calculate the molarity of the acid. Okay, that's this kind of procedure to calculate the unknown concentrations by reacting solutions together in stoichiometric proportions is called titration.